Hi everyone, my name is Mohammad Shafiq and I work as a solution architect here at Mentor. In this role, I work with our customers to solve their problems using our broad product portfolio of embedded software and development tools. Today, we are here to discuss implementing Internet of Things and what it involves at a high level. So let's get started. I'll start with the assumption that you're familiar with the term Internet of Things and how it impacts us and everybody around us. So I'll not spend much time on discussing what IoT is. Instead, this webinar is to go a little deep and discuss IoT implementation aspects. From an implementation point of view, IoT can be defined as internetworking of a broad range of electronic devices that generate data. Data from these devices is collected, processed or analyzed and exchanged between different entities in this network. This internetworking and connectivity of devices allows us to derive useful results that are otherwise not possible if working with individual devices. This is a simple but a very broad definition of IoT with almost unlimited scope, as there is a wide spectrum of devices that can be interconnected. There are different ways that these devices can be connected. There are different technology components that can be used to process and analyze the data collected from these devices. Then there are different options to showcase and present these drives results to end users. So when put together, overall it becomes a complex system composed of many different technologies, and especially for beginners, it becomes relatively difficult to start their IoT journey and construct a big picture in their mind. That's the problem that we are going to help with today. So let's start with a simplistic view of an end-to-end IoT implementation. This slide shows a simple view of an end-to-end IoT implementation. Although there can be variations, but we should be able to relate this model to most of Internet of Things implementation, from smart home or consumer electronics to medical or industrial IoT. We'll use this diagram as a basis of our discussion throughout this webinar. As you can see, at a high level, we can broadly divide IoT implementation into two domains. On one side, we have collection of electronic devices or things that mainly work with embedded systems technologies. The other half relates to backend servers or cloud services that mostly operate in web technologies. So starting from the right side, we have edge devices that can be sensors or actuators that are generating or consuming data. Then we have special type of devices in the network that are called gateways. Then we typically connect these devices or gateways to remote servers over IP-based protocols using public internet. Then on the left side, we have cloud service or data center where we store and analyze data from the devices in the field. The last component to discuss is the presentation of data or the user interface. We'll take a closer look into these 5 components one by one in the remaining slides and discuss briefly how they relate to each other. So let's start with the device or things in the system. From implementation perspective, these are embedded devices with typically low compute power. There is a broad choice of processors or CPUs that can be used to realize these devices. These can be tiny MCUs or rich multi-core processors. Then there is a broad range of technologies available on how to program these devices and what type of embedded software to put on these. Tiny, low compute MCU-based devices can be running low footprint real-time operating systems like Nucleus, or in some cases, they might be running bare metal code. In cases where there is substantial compute power available on these devices, these can run embedded Linux or other rich runtime software. In addition to base runtime or operating system, there is a wide variety of networking options available on these devices. These can be IP-based protocols, or these can be specialized local proximity networking protocols. We'll discuss these in a bit more detail later, so I'll leave it at this for now. In addition to runtime and protocol stacks, there are various device-side frameworks available for IoT devices. Few of them are listed here. IoT is an open source implementation of Open Connectivity Foundation specifications that allow various devices to communicate with each other in a standard way. LWM2M, or lightweight machine to machine, is OMA specification that facilitate implementation of device management functionality on an IoT device. All join project is similar stack as compared to IoTVT and is now on course to merge into the overall Open Connectivity Foundation specifications. There are other similar device-side frameworks available that can be integrated on an IoT device. One observation to make is that devices that participate in Internet of Things have broad spectrum, with tiniest devices used for telemetry or gathering low-frequency data, to huge industrial units that are part of complex industrial processes that are generating large amount of data. So one device can be very different than another device in implementation and with respect to supported feature set and complexity. This slide lists some of the key functions that needs to be implemented or can be implemented on an embedded device. So the first category is onboarding or device discovery or provisioning functions. So these are required for any of these devices to be part of the network. Then we have data services that are help send messages from device to the cloud or send control or commands from cloud to devices. Then for the rich set of devices, we can implement device management functionalities that can allow us to remotely configure these devices or reset these devices or do firmware updates on these devices. So depending on what type of system you are building, your device side implementation can vary a lot. Let's now talk about gateways. In a way, gateways are special type of devices that we just discussed. So all the device features, functions apply to gateways. These devices have typically medium to high compute power. In addition to standard device functionality, gateways facilitate network by creating a localized subnetwork. There can be many driving factors to have a subnetwork. For example, gateway can enhance security in the system by providing a single point to control, configure downstream devices. This can reduce the attack surface for the network and improve security. Gateways can aggregate and filter data that they received from the local devices before it is sent to the cloud. One important function that gateways can provide to the network is the address and protocol translation. For example, if the devices are talking Bluetooth or Zigbee protocol that cannot directly connect to IP network, gateways in this situation help by receiving data locally on Bluetooth or Zigbee, but then translating it into IP protocols and sending to the remote servers or the cloud. Gateways can also contain some extra functionality, like they can do some local logging or network monitoring. Now let's briefly discuss IoT components where we have to deal with web technologies. We can start with cloud service first. Cloud service or backend data center is basically a large group of compute or storage servers that have been networked together. So if you want, you can set up your own data center by purchasing your own hardware and set up it as a cloud. That would be called a private data center or a private cloud. Alternatively, there are vendors like Microsoft, Google, or Amazon, and many others who have already set up huge data centers around the globe, and you can purchase subscriptions to use those resources. There are few features that make data center a cloud that are important to note. For example, these compute or storage resources should be available on demand when needed instead of them being make or break fixed resource setup. These server resources are available to scale with requirement. So there is a concept of having elasticity in them. The pricing in the cloud is also based on the usage of resources instead of a fixed price per unit. So why do we need cloud service as part of IoT system implementation? There are multiple reasons for that. First one is to act as a hub or aggregator of the data received from all the devices. IoT can scale to devices in millions or more, so the cloud service provides a common point to ingest all the data and scale the network. The second use is to provide storage for a huge amount of data that's generated by the devices. Then there are enormous amount of compute resources available in the cloud that can be used to analyze and process this data, or the cloud can host the applications or the presentation layer for this data to be visualized for the end users. This is a very simplistic view of the cloud service and the functionality it provides. There are hundreds and hundreds of technology components available in the cloud, and more are being evolved every day. So different type of databases, different type of analytics engines are being developed that are available through the cloud services. Next component is the presentation or the user interface into the IoT system. This component has become an important part of IoT system because of proliferation of smartphones, tablets, and richness in browser technology. Presentation or user interface for IoT system is done via web or mobile applications. This is the interface where humans actually interact with the system either to configure or monitor or to add input or to visualize results. Web application are basically the type of application that run in client browsers. So they scale pretty well from smartphones to traditional desktops or PC. Native mobile apps, on the other hand, are specific to a mobile platform. For example, for iPhones, this will be an iOS application. You can also build hybrid applications where you start with the native mobile application, but then use web application technologies. Let's talk about a bit more about the web applications. So web applications are implemented in kind of two parts. One is the client side that actually runs or interpreted on your browsers on smartphones or tablets. For example, you get an HTML page and your browser is responsible for parsing the tags and displaying a resulting view. The other part of application is the one that runs on the application server hosted on the cloud. Previously, we discussed cloud receiving data from devices, storing and analyzing it. Then the processed data is fed into application servers so that it can be sent to client devices for human interactions. On the client side, you have various technology components, for example, HTML style sheets, JavaScripts, Ajax, or jQuery frameworks to write your application. On the server side, there is a large number of frameworks available that come from different vendors, open source or proprietary. It includes .NET, C# technologies, PHP, Cold Fusion from Adobe, or Python, Perl, Ruby on Rails. So there are hundreds and hundreds of frameworks and tools available in this area. This is just kind of a small list of available frameworks that can be used to build web applications. Then we have mobile native applications that can either be written in native development environment. For example, for iOS, that would be Swift language or Objective-C, and you use Xcode IDE from Apple. For Android, you can use Android Studio IDE to program your applications, and mainly you'll write code in Java. In addition to those native platforms, over time, some very powerful uh, cross-development platforms have emerged. Some of them are listed here, like Xamarin, Iconic, React Native, etc. These platforms enable reuse of code across various platforms. Using these platforms, most of the code that deals with look and feel and business logic is shared, and the only platform-specific code needs to be maintained separately. Now let's discuss connectivity in an Internet of Things system. Connectivity is a huge topic for Internet of Things, and I would like to highlight connectivity in terms of access network and proximity networks. So access network is typically IP-based connection that is utilizing public internet infrastructure. Proximity network is a local network of devices that's typically behind the gateways. This can be IP-based, but in a lot of cases, this can involve other technologies. Let's talk about access networks first. The protocol used in access networks need to be supported both on device and cloud side, because access network is connecting the web technology world to embedded system devices. So if it's a client server model, then server can live within cloud and devices can be client. Or if the protocol is horizontal, then it can be same stack that needs to run on both device and clouds. Now, the top four protocols to provide connectivity from device to cloud are HTTP, MQTT, AMQP, and CoAP. HTTP is well-known application level protocol that's widely available and supported on internet, but it's not much suited for IoT use cases due to its need for compute resources, reliability concerns, and performance issues. MQTT is publish subscribe lightweight messaging protocol for small sensors and is optimized for high latency or unreliable networks. Initial specification for this protocol came from IBM. AMQP is a protocol that came from financial industry and the corporate world, and it's very well known within web services or web technology world. CoAP is a web transfer protocol much like HTTP for use with constrained nodes and constrained networks. In the other protocols, OPC-UA is interesting and important in context of industrial Internet of Things. XMPP is another protocol that has its origin in chat and messaging world. I've also seen implementation where people have used VPN technologies to create a private network between cloud and devices. Some implementation use WebSockets to build a responsive application. So that's another protocol that can be used in access network. Proximity networks have numerous options. I've listed them in two broad categories with Wi-Fi, Bluetooth, Thread, Zigbee, 6-LoWPAN, Z-Wave, NFC, RFID, and infrared, more suitable for smart home or consumer electronics. Whereas there is a whole category of protocols that are used in the industrial world. So there are many more that are available that can be used as proximity network, but I'll not go into detail due to time limitations. So this is another view to visualize the protocol usage within IoT system. One thing to understand is that this slide provides a typical usage scenario for these protocols, but in some cases, the protocol used to form an access network can also be used for proximity network. For example, you can set up a web server on your gateway and have your proximity devices talk to it as HTTP client. Or you can set up an MQTT broker on gateway and have downstream devices talk MQTT. So this slide basically provides you a kind of general view where different protocols fit in, but you can see variations in some Internet of Things implementations. One more terminology that I wanted to explain is fog computing and where does it fit in. So what we have discussed so far is end-to-end implementation, and now we want to see where does the fog computing fit into this implementation. Then, interestingly, Open Fog Consortium has a very broad definition of fog computing that suggests that any compute, storage, or network resources that are not part of cloud or device make up fog. Typically, these resources are placed near devices to increase response time and reduce their immediate dependency to cloud. And for example, we already discussed gateways performing logging and filtering functions close to devices before the data is sent to the cloud. So those can be some examples of fog computing. You can add more compute resources near the device. Like you can put a database server or an analytics engine within a server near the devices to provide a quick response. That would be another example of fog computing. So we started with a very simplistic view of IoT implementation, but as you can see that due to wide range of options, the overall view becomes quite complex. And there are different type of technologies involved in implementing an end-to-end IoT system. So the question is, how do you go about implementing IoT? The good news is that there are many commercial solutions available in the market that help simplify this implementation. So on the web or cloud side of things, there are IoT platforms that integrate many of the components and make them available to the IoT implementers. And on the embedded side, we have multiple solutions available where a large number of building blocks are already integrated and baked together so that it facilitates building an IoT system. Let's take a brief look at examples of such solutions, both for cloud and embedded domains. This slide provides us a very summarized view of Microsoft Azure Cloud Services. There are more than 100 services available that facilitate implementing cloud or web or mobile application side of things. So you can see on the bottom there, Microsoft Data Center is spread across the globe, and then you can buy a subscription to Microsoft Azure and pick and choose building blocks available and make them part of your IoT system. For the device side implementation, we have vendors like Mentor Graphics that facilitate implementing device side of IoT by providing pre-baked embedded software solutions. These include real-time operating system, embedded Linux, or other software stacks required to implement your IoT devices. In addition to software components, Mentor Graphics also provides tools and services to help customers build their devices. Mentor Graphics has also taken a step further and integrated the embedded software stack with cloud environments like Microsoft Azure, so that you start with a strong footing to get your IoT device implemented and can focus on your application development right from get-go. In fact, Mentor Graphics has capability to get involved with customers implementing IoT systems from concept and take them through proof of concepts, design and development, verification, and all the way to post release support.